Hello there guys, and welcome back to another epic inexorable maths video. In this video we're going to find the radius and interval of convergence of a very famous series, a very famous power series, and I'm going to do plenty of videos on this. So this is a continuation, a crossover event, you could say, of two playlists that I've got. And the first one is Taylor series. You could also say Maclaurin series maybe with that too, but also convergence tests. So in order to know what the radius or interval of convergence of a power series is, which I'm about to explain, you're going to need to know what is a Taylor series, and you're going to need to know what is a convergence test, or how do you do a convergence test. So as long as you know those two things, I'm going to leave the links to the description, and both of those playlists will be in the link in the description. But as long as you know both of those things, then you are all good, and we can get started. So first of all, what is this? What is this? Because this is the first video that I'm doing on this topic. So what is a radius of convergence? What is an interval of convergence? I'm going to explain it with an example, okay? So I'm going to begin by writing down the power series for the function e to the x, and I'll label it e to the x, I'll call it e to the x, and that is equal to the sum from r equals 0 to infinity of 1 over r factorial times x to the power of r. And again, this is centered at the origin, at 0. Now, this is the standard Maclaurin series for e to the x. It's pretty standard. Hopefully everyone is pretty happy with this, okay? But a very valid question is this series, is this version of e to the x really valid for any value of x? Because you must have already been familiar with a geometric series, and of course the idea of whether a geometric series converges or diverges, and more broadly, the idea of any series converging or diverging. So is it really very obvious whether, if I choose x to be maybe the number 1 billion or a massive number like that, is this really the same as e to the x, or will it diverge? And what the interval of convergence is going to tell us is what range of values can I actually plug in to my Taylor series for the Taylor series to be valid and to work. Because some of them are valid for any real number, some of them are valid for not any real number, and actually values that are smaller than or equal to a certain other value, or something like that. The radius of convergence is basically just, essentially, if you imagine an interval, it's half the interval and it's just the length of that. But I'm going to give you a concrete example with this right now, and I'm going to walk you through how do we find it, and I'm going to tell you something really interesting, and it is true, you may have heard, but this is valid. E to the x, this power series, is indeed valid for any real number, and in fact, any complex number as well. And I'm going to explain that to you right now and how to do it. So we have to use our ideas from the playlist that I've made on convergence tests, or maybe you already just know what a convergence test is. So I want to show or find the range of values of x for which this converges. Now, in my opinion, the best test to use here, the majority of the time actually, is the ratio test, okay? So I'm going to assume that you already know what the ratio test is. As I go through it, I will explain it again briefly, but it's good to already know what the ratio test is. And I have plenty of videos on the ratio test already that you can check out at your own discretion. So what I'm going to do is I'm going to consider, and I'm going to do this in a different color here, I'm going to consider the limit as, we're going to go r approaches infinity of the absolute value of the ratio between the two terms. The ratio between between the next term and the previous term that you're on. So the r plus 1th term divided by the rth term. Okay, so the r plus 1th term is going to be, and I'm going to write these as fractions here, so I'm going to go x to the power of r plus 1 divided by r plus 1 factorial. Hopefully you can see that that would be the next term, and the standard nth term or rth term is just going to be x to the power of r divided by r factorial. okay? What do I need for this to converge? Because we don't, I mean, you know, you might say, well, it depends on what x is, what this is equal to, what this limit is equal to. Well, in order for the ratio test to come up and say, this is a convergent series, this number needs to be less than 1, okay? So we need this to be less than 1. And we're going to solve this for x, okay? That's the difference, I guess, between how this normally works and how this is going to go right now. So we're actually going to solve it and find which values of x will this actually be less than 1 for, okay? So this limit is equal to the limit as r approaches infinity of, and then let's clean this thing up a little bit. So I'm going to write this, and again, I'm going to assume that you're pretty happy with how to use the ratio test already. I'm going to simplify this as follows. And my r's are not very good, guys, but hopefully you can see this is an r and this is an r, believe it or not. Okay, and then we can keep going. And we're going to see what we get. So I'm going to cancel out the x to the r's, and I'm just going to have x, and then I've got an r factorial still there, divided by r plus 1 factorial, and a very common trick here is to rewrite r plus 1 factorial as r plus 1 times r factorial, so that I can cancel the r factorials out. And so I have the limit as r approaches infinity of x divided by r plus 1. Now, and that needs to be less than 1. Now here's the thing, guys. X is a constant. So even if it was a giant number, a massive number, as big as you want, this is still going to approach 0. Because any number divided by r plus 1 as r goes to infinity, it is going to go to 0, okay? So we see that this is true for all values of x. And we can use a bit of cool mathematical notation, all x. And actually, this is true for, you can imagine, any complex number as well. So even if x was like 1 billion plus 2 billion I, or something like that, it would still converge, okay? So I'm going to just consider the real numbers for this, because we're not going to do any complex analysis type stuff, but I want you to know that this is also valid for complex numbers too. I'm going to say x is all x in the real numbers. But technically it is the complex numbers as well. I just don't want to bring complex numbers into this video, but it is true for complex numbers as well. That means that the series for e to the x, this one here, this is true for any value of x. It's not like a geometric series where if the common ratio is too big, then it will diverge. X can be as big as you want and it will always converge, okay? So what does that mean? Well, in terms of the interval of convergence and the radius of convergence, it means that we can say the interval of convergence, because they're kind of the same thing, but just different ways of thinking about it. Interval of convergence. We could write that as just x has to be between minus infinity and infinity. We could say that's the interval, minus infinity to infinity. And the radius of convergence, the radius is not an interval, it's a number. So the radius of convergence, oh, my handwriting has gone a little bit down the drain there. Convergence is, we normally use the capital letter R to stand for the radius. And I'm going to explain the radius word in a second, but the radius is just equal to infinity. It has an infinite radius of convergence. Now, many people say, what's the deal with the word radius? Why are we talking about a radius? How, you know, it sounds like you're talking about circles or something, right? Radius. Well, it's because we are imagining that we're dealing with complex numbers here. So what I'm saying is, let's say the radius of convergence for a different series was that r is equal to 3 or something. So that means that if the size, if the modulus or absolute value of the number was any bigger than, let's say, 3, then the thing would diverge. Then you could almost imagine it in the complex plane on an Argand diagram as, and that's a very bad circle, of course, but here's our real axis, here's our imaginary axis, if you know anything about complex numbers. And so it literally is a radius, it's a circle, it makes a circle. If you're inside the circle, any complex number inside the circle converge, any complex number outside the circle diverge. And that's why it's called radius. If you're only dealing with the real numbers, then it's an interval, isn't it? Because it's not a circle, it's not really a radius, it's just an interval. So it's basically, we just consider it to be, this is the radius. Or you could say this one as well, the radius, because it's this half, it's the distance that the number can be from the origin. Okay, that's where the word radius comes from, if you wanted to know. Now, that's a brief introduction to the radius and interval of convergence. I'm actually going to do this for all sorts of series as well, so stay tuned for sine, cosine, and all the ln ones, arctan, we're doing them all. So stay tuned, let me know if you found this video helpful. Please let me know as well if there was anything that I could have explained better or blah, blah, blah. All that stuff, I want to hear it in the comments. But amazing, e to the x, we know this guy is valid for any value of x. That's pretty good stuff. Thank you so much for watching as always, and I will see you in the next video. Cheers.